Hello, everyone. I'm Dr. Sahan Perera, presenting the research on resilient moduli responses of PET plastic bins with demolition waste. Moving on to the introduction and the materials, which are construction and demolition waste, polyethylene terephthalate, which is PET plastic waste, CND and plastic blends, and methods, and laboratory test, which is comprised with evaluation of geotechnical parameters, evaluation of resilient parameters, and evaluation of bulk stress model parameters. Results and discussion, conclusion, and references. Okay, moving on to the introduction. When we're talking about the CND waste, the 8.7 million of concrete aggregates are annually stockpiled in Australia, and 6.71 million tons of construction and demolition waste, and 7.39 million tons of municipal solid waste were sent to landfills in 2016. And 2.5 million tons of plastic waste generated in Australia in 2016, and 12% of them was only recycled. 87% of plastic waste generated in Australia was either sent to China or landfills. In 2016, 1.2 million tons of plastic waste was sent to China, and China banned plastic intake in 2017. Therefore, scientists predict 40% of increase of plastic waste into 2050, and Australia will face significant waste management crisis. And first of all, we move into the construction and demolition waste, which are comprised with RCA, recycled concrete aggregate, and CB, crushed bricks, which comprises the major component of the CND materials. RCA contains concrete and rock, while CB contains typically 70% of brick and 30% of materials such as asphalt and concrete. Moving on to the plastic waste. Here, the soft drink PET bottles usually have polypropylene cap bottleneck ring, and plastic labels are assembled around by using adhesives. The plastic containers were washed and dried and shredded into 5 mm particles using a Zerma granulator. And this is the granulator, and these are the shredded plastic flakes of 5 mm particles. And these are the blends which are used in this research. As an example, here 5% PET, 95% RCA, and third blend without 0% CND. So all the percentages are calculated using the dry mass of the materials. CND and PET considered as control materials, which will be added up to 100%, while cement or other binder content percentage was defined with respect to dry weight of the basic materials. Moving on, the RC and CB had 20 mm particles, maximum particle size, and the PET had 5 mm particles. And here you can see the ABC depicts the naked eye view, and DEF depicts the microscopic view of the material. And PET depicts a smooth surface, while RC and CB, which with respect to RC and CB, which reduce the interparticle friction of CND and particle PET blends. Higher percentage of wooden particles are observed in RC than CB samples. Moving on to the results and discussion. First of all, the particles distribution. Through 3 control blends and the mix of PET and CND blends were used for the basic categorization test. According to this figure 2, CB blends contain higher percentage of finer particles than RCA. Adding 5% PET had negligible effect on PSD curves or grading characteristics of the PET and CND blends. Moving on to the modified Proctor compaction of the blends. The modified Proctor compaction of unbound and 3% cement stabilized blends are presented in the figure. And the maximum dry density values of the cement stabilized blends are higher than the respective unbound blends. The fine cement particles can fill the voids in blends and increase the MDD, or the maximum dry density of the blends, producing better compaction. Adding 5% PET in blends has reduced the MDD values and increased the OMC values of the CND materials. Moving on to the evaluation of resilient parameters, the resilient modulus of MR of the RCA blends was determined by the RLT test, which defines the material response to traffic loading under existing physical conditions and commonly adopted as an input parameter in designing flexible pavements. The variation of resilient modulus of RCA blends and CV blends under 15 combinations of confining pressures and cyclic axial stresses are presented in this figure. The range of resilient modulus values of the RCA blends are summarized in the table. The resilient modulus values of the blends have been increased with applied confining pressure. The high confining pressure leads to high particle interlockings in soil. And moving on to the same resilient modulus values of CB blends are presented in this slide, and the resilient modulus values of RC and CB was compared and contrasted in the next slide. The RCA blend shows higher resilient modulus values than the CB under same confining pressure applied at 15 stages of the RLT test, or the repeated load triaxial test. Resilient modulus values of the stabilized materials are highly governed by the Los Angeles abrasion loss value of the materials used. CB shows a higher finer particle percentage and flakiness index value than RCA. Materials which have particles with high flakiness index and high finer percentages increase the surface area of the total material mixture. Such sample in stabilized conditions require more cement volume per contact material grains for the same cement content, hence resulting in low resilient modulus values. Adding PET decreases the resilient modulus value of the PORC and CV blends in both unbound and stabilized conditions. According to this figure, PET has a smooth surface when compared with the C&D material particles. Blending smooth surface materials has decreased the MR values of PET and C&D blends. And moving on to the bulk stress modulus parameters, AASHTO T3097 suggests that bulk stress model, which follows the equation 1, is suitable to predict resilient modulus of the granular materials, where MR, or the resilient modulus, is MR, and K and K2 are bulk stress model parameters, where theta is bulk stress. And the bulk stress model parameters of the C and B blends are presented in this slide, and the comparison is given in the next slide. According to the figures, previous figures, the log MR values of RC and CB blends and the theta model parameters of log K1 and K2 of the blends are presented in this table. And it's increased with the log theta values. Bulk stress of the sample depends on the applied confining pressure. Because of the high particle interlocking in high confining pressures of the log MR values of the blends have been increased with log theta. Bulk stress models of RCA shows higher K1 and K2 parameters than the bulk stress models of CB. And moving on to the next slide is the conclusion. And the study includes a suite of laboratory studies to evaluate basic geotechnical parameters and resilient parameters of the PET blends with RC and CB in both unbound and cement stabilized conditions. The gradient limits of RC and CB and associated PET blends were found to be within the limits set by Vicroads for the pavement-based sub-base materials. Adding 5% PET has close negligible effect on grading curves of RC and CB. Adding 5% PET reduced the MDD values and increased the OMC values of the C&D materials. Adding PET reduces the MR values of the RC and CB due to the reduction of frictional forces between the particles, especially when particles with high surface frictional resistance are replaced by smooth surface materials such as PET. Except 5% PET, 95% CB blends, all the other blends had a higher MR value than 125 MPa, which is the minimum MR requirement for pavement-based sub-base materials. And after adding 3% stabilization, those blends will satisfy the requirement. And the log K1 and K2 parameters of the bulk stress models of CFB suggesting RCA performs better out of the two tested parameters. Moving on to the references.